All right, so delta y is PR. And now I want to draw the diagram again one time. So here's Q, here's R, and here's P. And here's my triangle. And now what I'd like to do is draw this curve here, which is the piece of the arc of the circle. But really, what I want to keep in mind is something that I did also in all these other arguments, which is, maybe I should have called this orange, but I'm going to think of this straight line between. So it's the straight line approximation to the curve that we're always interested in. So the straight line is much simpler because then we just have a triangle here, and in fact, it's a right triangle. Right? So we have the geometry of a right triangle, which is going to now let us do all of our calculations. Okay, so now the key step is this same principle that we already used, which is that short pieces of curves are nearly straight. So that means that this piece of the circular arc here from P to Q is practically the same as the straight segment from P to Q. All right, so that's this principle that well, let's put it over here, is that PQ is practically the same as the straight segment from P to Q. So how are we going to use that? Well, we want to use that quantitatively in the following way. What we want to notice is that the distance from P to Q is approximately delta theta, right? Because the arc length along that curve, the length of the curve is delta theta, so the length of the green, which is PQ, is almost delta theta. So this is essentially delta theta, this distance here. Now, the second step, which is a little trickier, is that we have to work out what this angle is. So our goal, and I'm going to put it one step below because I'm going to put the geometric reasoning in between, is I need to figure out what the angle QPR is. If I can figure out what this angle is, then I'll be able to figure out what this vertical distance is because I'll know the hypotenuse and I'll know the angle, so I'll be able to figure out what the side of the triangle is. So now, let me show you why that's possible to do. So in order to do that, first of all, I'm going to trade the boards and show you where the line PQ is. So the line PQ is here. That's the whole thing. And the key point about this line that I need you to realize is that it's practically perpendicular. It's almost perpendicular to this ray here. All right? It's not quite because the distance between P to Q is non-zero, so it isn't quite, but in the limit it's going to be perpendicular. Exactly perpendicular, the tangent line to the circle. So the key thing that I'm going to use is that PQ is almost perpendicular to OP. All right, the ray from the origin is basically perpendicular to that green line. And then the second thing I'm going to use is something that's obvious, which is that PR is vertical. Okay, so those are the two pieces of geometry that I need to see. And now notice what's happening upstairs on the picture here in the upper right. What I have is the angle theta is the angle between the horizontal and OP. That's angle theta. If I rotate it by 90 degrees, the horizontal becomes vertical, it becomes PR, and the other thing rotated by 90 degrees becomes the green line. So the angle that I'm talking about, I get by taking this guy and rotating it by 90 degrees. It's the same angle. So that means that this angle here is essentially theta. That's what this angle is.